the quantum model, it is said that we can't know the exact positions of an electron in an atom. Instead, electrons are found in orbitals. Orbitals are regions of space where the electrons are most likely to be found. To describe the positions of these electrons, we use quantum numbers.
Quantum numbers are like the address of an electron inside an atom. The first, or principal quantum number, n, tells you in which main energy level the electron is in.
Values for n are positive integers, starting with the number 1. As n increases, the average distance of an electron away from the nucleus increases as well. In turn, the amount of energy that those electrons possess also increases.
The next quantum number, L, is the angular momentum quantum number. This tells you the shape of the orbital. For any given n value, the values for L range from 0 to n minus 1.
So for n equals 1, L can only equal 0. When L equals 0, you get an s orbital, which has a spherical shape. Now, for n equals 2, there are two possible L values, 0 and 1. Again, the L value of 0 corresponds to an s orbital, so there's nothing new there. L equals 1, however, denotes a p orbital, which has a degenerate dumbbell shape, like this.
For subsequent values of n, we get more and more values for L. In turn, there are more and more subshells. Here's a complete chart of all the orbital letters along with their values for L.
Now we'll move on to the third quantum number, ml, otherwise known as the magnetic quantum number. This number tells us about the orientation of an orbital around a nucleus. Values for ml range from negative L to positive L. Confused? Don't worry, we'll go through some examples.
So when L equals 0, you have only one possible value for ml. This means that there's only one way to orient an s orbital. If you think about it, this makes a lot of sense because s orbitals are spheres, and there's really only one way to orient a sphere in 3D space. For L equals 1, there are three possible ml values, -1, 0, and 1. As a result, there are three different orientations for a p orbital.
Lastly, we have ms, or the spin quantum number. Any given electron can either be spinning clockwise or counterclockwise. Another way of looking at this is that the electron is either spinning up, denoted by an arrow pointing up, or spinning down, denoted by an arrow pointing down. These values of ms are denoted by +1/2 or -1/2.
Note that the electrons aren't actually spinning on an axis. This analogy just helps us understand why only a maximum of 2 electrons can exist in any orbital at any given point in time.
Now that we know all this information about quantum numbers, we can derive the following table of electron quantities. Alright, now that we're done with quantum numbers, let's talk about orbital diagrams and electron configuration. These tell us a lot about the configuration of electrons within an element or ion.
When drawing orbital diagrams, there are 3 things that we need to keep in mind. The first is the off-fault principle, which states that each electron to an electron configuration will occupy the lowest available energy level. The second is the Pauli exclusion principle, which states that no 2 electrons within an atom can have the same set of quantum numbers. The third is Hund's rule, which states that electrons must be distributed among orbitals of equal energy in such a way that as many electrons remain unpaired as possible.
Now let's get to some examples. We'll start off with my favorite element, hydrogen, because it set off the fire alarms. Hydrogen has 1 electron, which is located in its 1s shell. To show this, you draw a box representing the 1s orbital and draw an arrow pointing either up or down inside the box. Since hydrogen's single electron is located in the 1s shell, the electron configuration of hydrogen is therefore 1s1, with a superscript denoting the number of electrons in that shell.
After hydrogen, we have helium, which has an electron configuration of 1s2. To display this on an orbital diagram, we draw 2 arrows in the 1s box, one pointing up and one pointing down. This shows that the electrons in the orbital have different spins, and therefore fulfill Pauli's exclusion principle.
Okay, now things start to get a little more interesting once you get to boron, carbon, and the other elements in the p block. To show you this, Here are the electron diagrams of all the elements from boron to neon. As you can see, the electrons first occupy the empty degenerate p orbitals one by one because they are repulsed by any orbital that already contains an electron. Afterwards, additional electrons complete the pairs, as you can see in oxygen, fluorine, and neon.
When writing electron configurations and drawing orbital diagrams, it's important to always keep the off-bound principle in mind. That is, that electrons in an atom always want to occupy the lowest possible energy level, or in other words, the orbital closest to the nucleus of the atom. Now, you might be thinking, how do we figure out exactly which orbitals are the lowest possible ones that these electrons can occupy? Well, to do so, we refer to the following chart. On this chart, you can see that the electrons will first fill the 1s orbital, then 2s, then 2p, 3s, 3p, 4s, 3d, and so on.
Let's try some more electron configuration examples. My personal favorite is arsenic because it killed Madame Bovary. Arsenic has an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p3. That might seem excessively long, and that's because it is. But don't worry, there's an easier way of expressing electron configurations. Instead of writing the full electron configuration of arsenic, you can just write Ar 3d10 4s2 4p3. Ar acts as a replacement for the electron configuration of argon, and this way you can also focus on the valence electrons.
Alright, now let's try another example, tellurium, which is element number 52 on the periodic table. I'll give you a little bit of time to figure out the shortened electron configuration for the element. Feel free to pause the video if you want some extra time. Do you think you've got it? Well, the actual electron configuration for tellurium is Kr 4d10 5s2 5p4.
As you may have noticed by now, when you write electron configuration, you always write it in the order of increasing energy. For example, 4d will always be written before 5s. So even though electrons in the tellurium atom are first added to the 5s orbital, the 4d orbital is still written first. This is because when electrons get added to the 4d orbital, it shifts down below the 5s orbital, making it of lower energy. Now, before we finish today, we still need to talk about the exceptions, because there are exceptions to almost everything in chemistry. The two main exceptions we'll be talking about today are chromium and copper.
Chromium is a transition metal in the D block. Due to its position on the periodic table, we expect it to have the electron configuration Ar 3d4 4s2. However, its actual configuration is Ar 3d5 4s1. To explain this, we have to look back at the off-bound principle, which states that electrons always want to occupy the lowest possible energy level. It then turns out that much less energy is needed to place one electron in the fifth and final d orbital than to pair two in the s orbital. A similar case stands for copper. Instead of having an electron configuration of Ar 3d9 4s2, it has one of Ar 3d10 4s1.
Here's a periodic table with a few more exceptions highlighted. These are exceptions for the same reason as chromium and copper. There's a few more, but you don't need to know them for this course.
Lastly, let's talk about how to write electron configurations for ions, starting with negative ions. Whenever you create a negative ion, always add electrons to the unoccupied orbital with the least energy. An example would be fluorine. Fluorine has an electron configuration of 1s2, 2s2, 2p5. Therefore, fluorine 1- has a charge of 1s2, 2s2, 2p6. The extra electron is added to the 2p orbital, because that is the unoccupied one with the lowest energy. Similarly, when writing the electron configuration for a positive ion, always take away electrons from the occupied orbital with the highest energy. For example, since lithium has an electron configuration of 1s2, 2s1, lithium 1+ would have an electron configuration of 1s2, with the electron in the 2s orbital being taken out, since 2s has the highest energy of any of lithium's orbitals.
And that concludes our lesson for today. If you still need to review a specific topic that was mentioned in this video, please pause the video and click on one of the links right now. And if you still don't understand anything that we talked about in this video, please message one of us and we'll provide you with a free box of tissues in preparation for your upcoming chem test. Please tune in to the next episode of Lily Yang, the Science Orangutan, where we'll be discussing the gun pen trade in Afghanistan. Thank you for watching!